I'm going to talk about concurrency, specifically functional concurrency, with emphasis on the word functional. At first, what is it that we like about functional programming? We like composing functions, ideally pure functions where the input and output types are the only interface of a function to the external world. No hidden channels of communication. On the other hand, what we really don't like are side effects. And that is because side effects make it hard to reason about code. Now, what does concurrent functional programming look like in practice? We start a bunch of sequential processes. These come under many different names, like processes, threads, actors, fibers, and so on. And we let them communicate via side effects. And it doesn't matter whether, oh, maybe it does matter, but writing to a shared mutable state is a side effect, and likewise sending and receiving messages are side effects. So do you get the irony here? We are building functional concurrency on top of side effects and sequential processes. And how do these threads compose anyways? So, composing functions is nice and feels like this. The pieces fit nicely together thanks to types, and when we are done, a lot of times we have it correct already. Whereas composing threads feels more like this. We just start them, place them next to each other, and hope for the best. And what we get looks more like this. So my claim is we still don't know how to do concurrent functional programming, but let's keep trying. This time with these goals in mind. Can we compose concurrent programs the same way that we compose just pure functions, without any reliance on side effects for starting a thread or sending a message or communication in general, and without any manual thread management, any two things that don't depend on each other are implicitly concurrent. And these goals are exactly what Libretto, a concurrency DSL embedded in Scala, is all about. So the plan for today is to give you a taste of Libretto and then apply it to a well-known Santa Claus problem, which is a model problem in concurrency. Let's start with the list type that we all know and love. A list can be either empty or non-empty, and it's up to the producer to make the choice whether it's empty, it's going to be empty or non-empty. Types in Libretto are interfaces of interaction, always between two sides, and by convention we will call the one above the interface the producer and the one below the consumer. So in list, it is the producer who decides how many elements there are going to be eventually. There could be infinitely many. This list is a live data structure that evolves over time. And also the producer decides when does an element appear in the list. Let's show some scenario of this interaction over the list type. Here I just expanded the definition. It's now up to the producer to decide which side it is. Let's suppose, sorry, I skipped too fast. Let's suppose it's decided it's going to be non-empty. So the interface of interaction now evolved to an element and the rest of the list. Let's iterate it once more. Now it's again up for the producer to decide whether it's already empty, or there's one more element. Let's say there's one more element, and this is our new interface of interaction. An important thing about Libretto is that interaction over all of these ports takes place concurrently. Based on just this abstract type A, we cannot yet tell what the interaction over A is. As far as we can tell, it can go either way and actually both ways simultaneously. So let's look at some concrete types like int, or more generally any value type. It flows in the positive direction from top to bottom. Ping is a simple notification that also travels top to bottom. What about this unit type 1 here? Well, there is no interaction happening over this one typed port. In the case of list ones, the producer decides it's the left side. That means there will be no more interaction going on. Here we have a concurrent pair as an element type of a list. Int flows from producer to consumer, and ponk is dual to ping. It's just a notification that flows upwards. So here, for every element of a list, the consumer gets an int and sends a notification backwards. Let's do map on a list. Here I just expanded the definitions, and now we are going to branch based on the producer choice. Each of these colored segments, or only one of these colored segments, will actually execute. If it's the left case, that means the input was empty. That's easy. We produce an empty list by injecting to the left. If there is an element, we can immediately advertise downstream that we are going to produce a non-empty list. And meanwhile, or I should say concurrently to that, map the element by the given function and call ourselves recursively to map the rest of the list. Here's the code for this piece of diagram embedded in Scala. It's written in 0.3 notation just to highlight that this 0.3 code corresponds quite precisely to the diagram, but we can also write it in a more pointful way with variables and pattern matches. Now this highlighted part here is what this diagram reduces to after the producer has produced one element. So let's iterate it at a few more times. Another element, another one, and another one. And all of these mappings of elements take place concurrently without having to manually start and await any threads. Now, what happens if in the definition of list we swap the producer choice, that's down there, sorry, for a consumer choice. It's now, the interaction here is now driven by the consumer who can either close, that is, it doesn't want any more elements, or ask for the next element. And the producer always has to oblige and be able to produce the next element. And the consumer can repeatedly ask for more and more elements. That's why I call it endless. We have already seen ping and pong, which are just notifications that travel downwards or upwards. And these are dismissible, meaning we can ignore them. But since Libretto is linearly typed, we have to do that explicitly using a provided operation to ignore ping and pong. These have everything has to have a type, but we often omit this one-typed ports, unit-typed ports in the graphical notation. There are also non-dismissible signals which represent something expensive that has to be awaited, like some I/O operation. We cannot just fire and forget. So an I/O operation, if it doesn't produce any value, it would still produce done, and we have to await it somehow. Let's look at some of the ways signals can be introduced. This is not exhaustive, but if we already are awaiting something expensive, we can also send sideways a notification, the dismissible notification, as long as we keep awaiting the expensive computation or I/O. Here, this is producer choice, so the choice is going to be made here from above and propagated downstream, but we can get a notification of when the producer made up its mind, whether it's left or right. And when it does, when it chooses, say, B, we get the ping here, but also propagate the B downwards. Pings can be used to defer some propagation of information. Let's look again at producer choice. The producer might already make up its mind that it's going to produce B, but we can defer the propagation of this information downwards until also a ping arrives here. All of these have counterparts for pongs, for the other direction of data flow. In the case of consumer choice, where the consumer from the bottom chooses which side it is, we get a pong notification on the side, and likewise can defer propagation of the choice made by the consumer until also a pong notification arrives. We can abstract this ability to produce notifications or be deferred by notifications into a type class, if you will. And once we have types A and B, where A can produce a notification and B can be deferred, and until some notification we can sequence B after A by composing them. Racing. When two events are concurrent, it's non-deterministic which one we observe first. But nevertheless, we might want to choose a different path in our program based on what happened first, or what we observed as happening first. And for this, there's an operator to raise two notifications, and out we get one bit of information, whether the left one won or the right one won. And there will be no interaction over these unit-typed ports. Using this basic building block, we can build a racing operator for any type that is able to give us a ping. So we obtain the pings, raise those pings, and then bring the original A and B into each side of into each branch of this producer choice. We are again omitting the one typed port down here. Notice that whichever wins the race, on the left it's the A, on the right it's the B. We cannot just ignore the other one. We still might have an obligation to await or do something, to consume the other one. All right, let's use that racing for something. Here we have runners that are registering for a marathon, and as they register, they appear in a list. In this case, 4 runners have already registered, and there might be more coming. Remember, a list is a live data structure that evolves over time. Each runner will emit a notification when they complete the marathon. On the output, we would like to have runners appear in the order in which they complete the marathon, which, of course, can be different from the order in which they registered. And we want them to appear as soon as they finish. So our task is to implement this sort by signal function here. We'll keep it simple and do insertion sort. If the input list is empty, that means no one has registered and no one will ever register for the run. We output empty list. If at least one person registered, we recursively sort the tail of the list and then insert this first runner into the sorted list. Here's the insert. So now we have a runner and a sorted list of runners. We raise them. So the runner sends us a notification when they complete the run. A list sends us a notification as soon as it's decided whether it's empty or non-empty. In case the runner signals first, we output it as the winner of the marathon. In case the tail signals first, that means the registration has closed and there's no more runners, in which case we output just the one that we are inserting, but delay its appearance in the output list until it also completes the marathon. And if the list that's signaling has an element, remember it's a sorted list, so it's a winner from this list, so we output this as the overall winner and do the insertion recursively. This code should not be surprising. It's similar to what you would write in a functional language, but it's interesting to consider what happens here at runtime. Because list is a live data structure, so all those registered runners that haven't completed yet, they are hanging somewhere in there, and there's some structure built up, and as soon as they fire, meaning complete the race, they bubble up through some local rewrites and appear at the head of the output list. Last bit of building blocks that we need to introduce is duals. They have a formal definition, but let's use examples. We've seen ping and pong, and these are duals of each other, which just means if we have a ping flowing downwards, there's an operator to invert its flow upwards as a pong. And likewise, if pong travels upwards, we can invert it to flow downwards as a ping. Perhaps more interesting is the duality of producer and consumer choice. If the producer that's making a choice here from above decides it chooses right, that is, it's going to produce B. We propagate this decision to the respective consumer choice. Here we are a consumer, so we choose that we want to pick the dual of B and connect those using here we are assuming they are duals, so using the inversion from that witness of that nested duality. And it's similar, the other inversion is similar. The consumer here is making a choice, says it chooses A, and so on the other port it's producer choice, so we produce the A. Well, this was dual of A. And one more bit, Libretto gives us ability to talk about duals without knowing what the concrete types are. So here we don't know if it's a ping, if it's a producer choice, but there's just this polymorphic type that denotes a dual. And we have these inversion operations on it. which leads to having two different duals for some types, such as a dual of ping is both minus ping and pong. Dual of producer choice is both minus producer choice and consumer choice, but these multiple duals are necessarily isomorphic. Okay, let's put them to some use. We can define non-empty list by just having a distinctive element and a potentially empty list. I'm going to show you just one function that we can define on a non-empty list, and that is borrow an element from non-empty list, but we have also the obligation to pass it back, or to pass some element of the same type back. There always is one element in a non-empty list, and at the other output we eventually get all the original elements, or the same number of elements, because all of them are returned. So how do we go about this? Expanding the definition. Now, we use the inversion, the polymorphic inversion, to, out of thin air, make a port for minus A and A. Think of it like a particle and an antiparticle springing out of thin air. Now, on the left, we already have what we wanted. And on the right, as the element is returned, we insert it back to the list, obtaining a non-empty list again. And we're using insert by signal. That is, it might take some recovery. It might still be in use, but we know it's going to come. And when it comes, it will appear in the list. Yeah, and thanks to linear typing, the consumer here really cannot ignore this obligation to return element of the same type back. Here's the code for that. Basically 2 lines. Now let's do a version. Let's introduce some type safety. What if the element that is used by the consumer here changes type, so that the returned element, the used element, has a different type? So we do that, and the only change we need to do is to reset the returning element using some provided function f back to a fresh element that can be borrowed again. Okay, so we can borrow elements. Or we can borrow one element. Can we borrow any number of elements? Well, sure. Let's just iterate the borrowing. So we are going to provide an endless supply of borrowed elements, given a potentially limited supply of elements. Endless is a consumer choice, where the consumer either closes or asks for the next element. We also bring this other output port to each branch of this consumer choice, and now we branch. The asking for the next element is the interesting case here. So we just borrow one from the input list, output it, and use recursion to service any further requests for borrowed elements. And we can do the variant with reset, where the returned element has a different type and is then reset before returning to the pool. Now, we have seen that concurrency is implicit if we want some sequentiality. What if we want to map an endless stream of elements so that we don't pull the next element from the input source until the previous one has been handled? Well, what does it mean, handled? But we will just ask the output element type to send us a notification of when it's been handled. So So expanding the definition of endless, and we branch. On the left side, that's not interesting. The consumer is not asking for more elements, so we close. On the right, we pull one element, map it using the given function, and let it signal to us when has it been handled. Now we invert this notification, this ping, into a pong traveling backwards. And remember that first, endless is consumer choice, and consumer choice can be delayed. The propagation of making a choice from downstream can be delayed by a pong. We have seen this block before on the choices, on the consumer choice. So yeah, we will not pull or even close the tail of the input source until the first element has been handled, and use recursion to map the tail of the source. So we see that sequencing things takes some extra effort. And this is a last bit of prep work before we get to a larger example. It's merging two endless sources into one, where if by the time the downstream is requesting next element, there's one already available from the preferred input, we output that one. Otherwise, we give a chance to the secondary input, and whichever element becomes ready first is passed downstream. So let's break it down. I said if an element becomes available, so first what element? So we're going to pre-pull one element, and then I said when it's ready. Oh, we already know this. We say it's ready. It's we use a say type class evidence to get a notification from the element when it's ready, get us a ping. And then I said by the time the consumer asks for the next element. Well, what time am I talking about? Endless is a consumer choice, and we have seen that this consumer choice can give us a pong notification when the consumer has made up its mind. So we obtain that, and we pass it upwards and invert it as ping. And now we're going to race these two elements and see which one wins the race. Right, whether the downstream is pulling first or whether an element from upstream, the preferred upstream, became available first. Let's say the downstream won, in which case we have to look, is it closing or is it asking for the next element? If it's asking for the next element, the preferred one is not ready yet, so we pull on the secondary source and let those two elements race, and then based on which one wins, we output that one. I'm omitting the details here, but the important thing here is that we turn some non-deterministic outcomes into a type on which we have to then pattern match and handle all the cases. So there's explicit case analysis of all the non-deterministic outcomes. Compare this to just having concurrent writes to a mutable variable. There are also all these cases, all these different orderings, in which order the writes would happen. But then the cases, the reasoning about cases that each ordering is fine is only in your head, whereas here it's turned into code, and we can trace like, oh, this case is here and it's handled this way. So it's more, there's more local reasoning here than just ordering, handling all the cases in your head. Okay, since you've been patient, now comes Santa Claus. Here's the problem statement, but I'm rather going to show you a picture. There are reindeers, 9 of them, which by default are on vacation. Then there are elves, 10 of them, which by default are in the workshop making toys. And then there is Santa, who by default is sleeping. Before Christmas, the elves return from vacation, and when all 9 of them return, they go with Santa to deliver toys. When elves get stuck on some R&D problem while making toys, they go to consult with Santa, but they have to form groups of 3 because Santa's time is too precious to spend it on just one elf. Here Santa at the moment is consulting with a group of 3 elves. If by the time this group leaves and goes back to work, if by that time all reindeer come back, then they have priority because it's more important to deliver presents on time than to consult with elves. Now, I have seen a few solutions to this problem in, say, in Haskell, in Erlang, in OccamPy, which is a language for concurrency. But all of these use the sequential process, say a thread or an actor, for each reindeer and each elf, perhaps some more threads. And then let them communicate via synchronization primitives or shared mutable variables, maybe transactional, but still shared mutable, or via sending messages. Here, let's do something different. And actually, we have already done all the hard work, so the solution fits on one slide. We have 9 reindeer and 10 elves, and we use our pool function from before that is going to present those limited numbers of helpers as an endless supply of borrowed helpers. Then we're going to form groups of all 9 reindeers or all 9 elves. I'm not saying what a group is, but that's an implementation detail. It could be just, again, just the list of 9 of these things. And then we use merge preferred that we saw before, which, if by the time Santa is ready to take the next group, reindeer group is already available, that one is preferred. So what does Santa do? It's quite easy. There will be some sequencing, because that's what the problem statement asks for, some mutual exclusion. So it's going to sequentially fold through this endless source. And if it's a group of reindeer, Santa goes to deliver presents with them. This gets us also a notification of when this action has completed. That's kind of like when the critical section has been exited. And then Santa releases the group of reindeers. Likewise, with elves, Santa meets with them in study and then releases them. When they are released, they travel backwards. Now the group is again disassembled, and we are returning back the reindeer here, and before we make them available, we send them on vacation, or send the elves to make toys. So, and this is it. There were no threads here, no side effects, and the solution is quite type-driven. Most apparently the pieces fit nicely together thanks to typed ports. But also, we have seen inside merge preferred or pooling, there was some racing, and we turned those non-deterministic outcomes into types that we pattern matched on, so we get some guiding from the type system of what we might do. And we could go further with type safety. Say, I loosely mentioned that a group could be just a list of borrowed reindeers, but it could be something completely different, like group 9 reindeers. Imagine a chemical reaction of 9 atoms forming a molecule. Now, these 9 atoms cease to exist as independent entities. They exist only as part of this molecule. Then this may, now they go deliver some toy that may transfer the molecule to some other form, and eventually they are released back into atoms, but this could be different atoms for exhausted reindeer versus well-rested reindeer. And this is the kind of thing that you don't even start to think about if a reindeer is a threat. Well, it's a threat and it's doing some side effects. So there's additional type safety you can get here. Let's recap some of the points of this Santa Claus example. Concurrency happens by default. How do we handle non-deterministic order of return? Well, it is inserting into a sorted list. That's quite a declarative statement. Forming a group, we just take the respective number of elements from the sorted stream. Easy. Priority of reindeers over elves. That's been offloaded to this merge preferred that we implemented before, so that does the heavy lifting. But how heavy? The most complex case was 2 nested races, so 2 nested pattern matches. And mutual exclusion of delivering toys versus meeting in study is handled by mapping sequentially, which we also implemented before, and is quite a functional way of expressing that problem. Now I'll point some friction points that you might encounter if you start programming this way. So we saw concurrency is seamless, but sequencing things can take some work. On the upside, though, if we find ourselves, we need to introduce explicit sequencing, maybe that just points to some missing causal link that we were neglecting, forgetting about before. Also, the linear types cause you to have to consume everything, and that can be annoying at times. On the upside, this prevents many resource leaks. You cannot just fire something up and then forget about it. Explicit, we had to explicitly, painstakingly handle the non-deterministic outcomes, but this is actually the way I prefer it, so that I can trace how each case is handled in code rather than, for example, again, mutate the same variable and then reason about the order of mutations only in my head. So to conclude, we have seen that it is, in fact, possible to compose concurrent programs the way we compose just pure functions. And in this process, we regained some of the type-drivenness. So I think it is time to liberate concurrent programming from the sequential paradigm of threats. And regarding functional concurrency specifically, it's time to liberate it from side effects. So let's make it happen. You can find Libretto on GitHub, including a running version of the Santa Claus example, and I can take your questions.
So, thank you for that. And so now, ladies and gentlemen, here comes our favorite question time. And for me, it's jogging time.
Dzięki. Thank you very much for the talk. Quite interesting, especially as an Erlanger and Haskell practitioner, so really offers you perspective on the practice. So I wanted to know if the question of triple modular redundancy was something that could be compatible with your approach. For example, ships have 3 chronometers when they are at sea. And if one or two, differ from the others, it's easy to, compare the results and do some code correction. So with the race and the merging, do you think this is something that could be applicable? For example, I have 2 databases which are like exact replicas, or rather 3 actually. 3 database replicas of each other and doing like 3 data retrieval operations and perhaps comparing them. Is this a pattern that could be implemented with Libretto, or am I trying to force it onto Libretto and actually it's a totally different concern?
So there was a lot. I'm not sure I got the question right, but I got that you were asking about databases, right? So this is all within one process, and with communicating with database, you will need to solve other issues like network connections, right? But the main point of Libretto is, okay, here we see we can do concurrency the way we do just pure functional programming. So the question is, okay, could we do more than just concurrency, and could we do network communication and distributed systems also declaratively, if you will, using something like just pure functions, like hidden, some ad hoc messaging? And I don't know, but I hope so.
Okay, who's next? Okay, no more questions. So thank you again. Another round of applause for Tomas.
There was one more question. Oh, never mind. There was one more question. One more hand I saw.
I'm sorry about this.
I think this is in somewhat of a similar vein than the last question, but maybe less leaving the abstract domain, which is how would you solve, for example, something where you have 3 things that can potentially fail or like return a unit or a proper result. You want like the majority, or you want like a majority consensus of these things. So you want more than half of them to succeed. Yes, thank you.
Right. Well, first you mentioned failure. So you model failure as you would in a pure functional programming. It's either error or the thing that you want. And then, okay, Libretto does not give you out of the box any implementation of a consensus protocol. So you would have to implement, well, okay, choose Raft and implement Raft in Libretto. It does not do any magic in this sense.
It's things that you can compose together.
Right, yeah.
Okay, is that all? So now you get an extra round of applause now.
Thank you.